Hello everyone. In the previous class we have discussed about reverse bias breakdown, in which we have discussed Zener breakdown and avalanche breakdown. In today's class we will discuss rectifiers. So in this we are going to discuss the piecewise linear approximation of a junction diode characteristics. So the rectifiers. So basically rectifiers makes use of a diode, and diode is a unilateral device. It is a PN junction and it is a unilateral device. Why it is called as unilateral device? Because it conducts the current only in one direction. As you know that diode has one junction, and when it is forward bias, diode is switched on and it conducts the current, and when it is reverse biased, the diode is turned off and it does not conduct. That's why PN junction is a unilateral device. The figure shows the piecewise linear assumption of a junction diode characteristics. There are three figures in this. That is, the first one, A, is the ideal diode characteristics, and second one, ideal diode with an offset voltage, and the third one is ideal diode with an offset voltage and a resistance to account for slope in forward characteristics. So as we know that PN junction is a unilateral device, the figure A shows an ideal diode as a short circuit when forward biased, and it is an open circuit when it is reverse biased. So figure A, observe the figure A, the IV characteristics. As you can see from the figure, so it is an ideal diode characteristics. So what is the characteristics of ideal diode? That is, an ideal diode as a short circuit when it is going to act as a short circuit whenever the diode is forward biased, and whenever it is reverse biased is an open circuit. So diode offers a low resistance when forward biased. As you can observe the figure, there is no resistance at all. So the complete current is flowing through the diode. That's why the characteristics is vertical to the y-axis. So diode offers a low resistance. Almost it is in ideal diode it is zero resistance whenever it is forward biased, and a high resistance when diode is reverse biased. So you can observe there is very high resistance and there is no voltage drop at all on the x-axis. So it offers a very high resistance whenever it is biased in a reverse. So an ideal diode, or you can also call it as a perfect diode, would have zero forward resistance and zero forward voltage drop. So it would also have an infinitely very high resistance, very high reverse resistance, which would result in zero reverse current. Although, but see here that ideal diode does not exist. Practically, we do not have any ideal diode. These are just the assumptions how the diode should be. Diode in forward bias, there should not be any resistance, and in the reverse bias, there should not be any voltage drop. That is an ideal diode. It is an assumption. So there are many applications where diodes can be assumed to be very near to the ideal devices. So in circuits with supply voltages much larger than the diode forward voltage drop, that is V, can be assumed constant without introducing any serious error. So see here that in circuits with supply voltages which are going to be very much larger than the diode forward voltage drop, that can be assumed a constant without introducing any serious error. So also along with this, the diode reverse current is normally so much smaller than the forward current that the reverse current can be ignored. So here the reverse current is almost equal to 0. That's why we can ignore them. See, so nearly it is an ideal diode, not exactly it is an ideal diode, because even a smaller current, reverse current, is available, then it's not a perfect diode or an ideal diode, but we can assume that it's a near ideal diode. So these are the assumptions that are going to lead to the near ideal or approximate characteristics for silicon and germanium diodes that you can see in figure B and figure C, in forward characteristics and reverse characteristics. So when the forward characteristics of a diode is not available, a straight line diode approximations, which is called as the piecewise linear characteristics, can be employed or can be used. So whenever the forward characteristics of a diode is not available, as like in a figure a straight line diode approximations, so which is called as a piecewise linear characteristics, can be used. So to construct the piecewise linear characteristics, V is first marked on the horizontal axis as shown in figure C. So see there, we have marked the axis V. Then starting at E0, observe the equivalent circuit. What is E0? It's a battery voltage. So starting at the E0, a straight line is drawn with a slope equal to the diode dynamic resistance. This is how a piecewise linear characteristics is employed. So an equivalent circuit for a device is a circuit that is going to represent the device behavior. So an equivalent circuits are shown in the below diagrams. Diode in the first diagram, forward biased, that is positive, V is applied to the anode, and positive is applied to the anode, positive of the battery, and negative is applied to the cathode. Like this we can make it forward biased and reverse biased. So an equivalent circuit for a device is nothing but it is a circuit that represents the device behavior. Usually the equivalent circuit is made up of a number of components, such as you can see from the figure, a resistor, a voltage cell, along with the diode. So a diode equivalent circuit may be substituted in place of the device when we are going to investigate a circuit that is containing the diode. In forward biased diode, is assumed to have a constant forward voltage drop and negligible series resistance. So in this case, the DC equivalent circuit is assumed to be a voltage cell. So this simple DC equivalent circuit is quite suitable for a great many diode applications like rectifiers and other applications. So an ideal diode can be placed in a series with an AC voltage source to provide the rectification of the signal. So what is rectifier? Rectifier is a circuit that converts AC signal into DC signal. We have different type of rectifiers: half wave rectifier, full wave rectifier, and bridge rectifier. In half wave, single diode is used. In full wave, 2 diodes are used, and in bridge wave rectifier we have 4 diodes. So since current can flow only in forward direction through the diode, the positive half cycle of the input sine wave are passed. In any of the rectifiers you take, what happens there? As current can flow only in the forward direction only through the diode, only the positive half cycle of the input sine wave are going to be passed through the diode. So the output voltage is a half rectified sine wave, whereas the input sinusoid has zero average value. So the rectified signal has a positive average value and therefore contains a DC component. So by appropriate filtering, so you might have studied the rectifiers. So after rectification, to remove the components, we are using what? A filtering. So appropriate filtering is used here to make it a complete DC signal. So by appropriate filtering, the DC level can be extracted from the rectified signal. Thank you for watching the video.